Hi everyone. So we just wrapped up one sample proportion and means testing. And today we want to look at hypothesis testing for two sample proportions. In the last two sections, we looked at hypothesis testing where we were given some status quo. So maybe we were told that the proportion of people who prefer dogs to cats is 37%. And we want to come up with an alternative hypothesis. Maybe we think it's greater than or less than 37%, or even just different from 37%. Or we're given that the mean height of men is 66.7 inches. And we want to come up with an alternative hypothesis to see if we could prove that with our sample. Now we're looking at hypothesis testing where we have two populations and we're comparing them to each other. So we'll start again with this null hypothesis, which is a statement of equality where the two proportions are equal, and then decide whether we think that they're less than, greater than, or not equal to. So one situation where you might use this idea is suppose you had a theory that the proportion of people who drive to work in South Carolina is less than the proportion of people who drive to work in Georgia. You would not be able to go to South Carolina and Georgia and ask every single person in the state, but you might be able to sample a group of 100 from each state. We'd start with the assumption that the proportions are equal, and then we would see if our sample data show that there's enough evidence that South Carolinians drive to work less than people from Georgia. So we'll go through our steps. So like I said, the first night of hypothesis testing is usually a little fuzzy, little abstract, but as we keep going through these steps, you'll see we follow the same process every time. The test just changes a little bit. So we want to start by setting up our hypothesis with the proportions equal, like we just said, and then our alternative hypothesis will be that we're either less than, greater than, or different from the other population, population 1 and population 2. The second step, as always, we set our level of significance, or our alpha. We do that at the beginning. Again, to keep ourselves honest, set the error early. Step 3, we want to check our conditions for both sample proportions. So now we have two sets of data. We're going to name one sample 1 and one sample 2. And for each set, we need to make sure that the proportion times the sample size is greater than 5. In most cases, that will be. And then we need a simple random sample and independent samples. Step 4, here's where things change just a bit. So we have new calculator directions. Instead of a 1 proportion z-test, which was number 5, now we're going to go SAT test number 6, 2 proportion z-test. And you can see here the big difference is we have two values for each sample to enter. So we have x1, n1, x2, n2. Then we just choose our alternative hypothesis, and we can solve for that test statistic and p-value. Step 5 is exactly the same as every other hypothesis test. If that p-value is smaller than alpha, we reject the null. And if the p-value is greater than alpha, we fail to reject. Step 6 is that last step where we bring it back to the initial situation. And so at that point, we say we either do or do not have sufficient evidence to support that the proportion of population 1 is either less than, greater than, or different, whichever your alternative hypothesis is, from the proportion of population 2. And so here's an example. We'll walk through step by step. In many colleges around the country, we have educators that are changing their approach to instruction from teacher lecture to a student-centered or lab model. In one school where this model was being introduced, of the 743 students who enrolled in the traditional lecture model, 364 passed. Of the 567 students in the student-centered lab model, 335 passed. Does the evidence suggest that the student-centered lab model results in a higher pass rate than the traditional model? And we want to use a 0.05 significance level. So we're going to look at these numbers. If we take it apart here, we have a student-centered lab model, and we have 335. That's our successes that passed out of 567. That gives us this is like our p-hat Although I think when I was typing this, I did not have the, I didn't have any way to write p hat, so I just called that p1 for our sample proportion. And then the teacher lecture model, we have another set of data. We have the success out of the total, and we get a new proportion. So we set our null hypothesis so that the two proportions are equal, and then our alternative hypothesis is that proportion 1 is greater than proportion 2. So we're saying that the success rate for the lab is greater than the teacher lecture model. Step 2, we're given the level of significance at 0.05. Then we take our n times p for both groups and make sure they're both greater than 5, and this is fine. Then we go to step 4. So we pull up the test statistic, and we're looking for the test statistic in p-value. No, calculator was not cooperating with me earlier today when I have the recorder up. So I'm just going to write this in here, assuming I can find my pen. There it is. Okay, so we want to go to stat, test, number 6. And that will bring you to this screen right here. And so that's our 2 proportion z-test. And you can see we put both sets of data in, 335 out of 567 for the lab-centered model, and 364 out of 742 for the teacher lecture model. And we have a greater than. And so when we hit calculate, that second screen pops up. We can double check our alternative hypothesis is correct. P1 is greater than P2. Our Z comes out to be 3.63 if we round. That's fairly high. That means it's a little over 3.5 standard deviations above the mean. So we would expect the area to the right. Remember, if it's greater than, it's a right-tailed test. So we have this idea where we're looking at 3.63, and the amount of area out here is very small. So we would expect the p-value to be really small, and that's what this p-value represents. Turns out it's 1.43, but we have that e to the -4. So we move the decimal 4 places to the left. We get 0.000143. Then we compare the p-value to the alpha. It's significantly less. Right? Way less than the alpha. So we reject the null, and then we bring it back to the initial situation. Since we reject the null hypothesis that the proportions were equal, we do have sufficient evidence that the pass rate of the students in the student-centered lab model is higher than those in the teacher lecture model. So that's the steps to run a 2-sample proportion test. And I hope that helps. And if you have any questions, feel free to email me, or I'll be around tomorrow morning for student hours, and then back for a problem session on Monday.